right, so good evening. Today we're going to be going over Chapter 7, Lessons 1 to 4, which covers geometry. But first I want to start with a review of Chapter 6 with some examples that we were working on last class. So this is the advertising example. And so I realized that when you read the question, it doesn't really tell you that a discount is applied. So there are really two ways to approach this question. I've done the examples both ways. One example where the discount is applied and the other example where the discount isn't applied. So with the first one, we're going to apply the discount. So let's read the example question again, or scenario again. It says Celino Advertising is furnishing a series of print ads for a client. Finishing the project will cost $2,000 per day for the first 7 days, and then $1,500 per day after 7 days. The finishing costs for a project taking longer than 7 days can be found using the following function. So C represents cost, and then $2,000 per day for the first 7 days. So we're going to represent the number of days with D, right? Because we don't know how long the project is going to take. We just know that we're being charged $2,000 per day for the first 7 days. So 2,000 times D to represent the first 7 days. And then we're going to add that because it's telling us to add $1,500 per day after 7 days. So let's say your project is going to take 8 days, okay? Then we know that we've covered the first 7 days with this information or this term on the left-hand side of our plus sign. And then the remainder of the 7 days will be represented by D minus 7. And since we decided, or we chose 8 an example, this half or this part of the equation would represent our 8 days, and we're just plugging 8 here where D is, so 8 minus 7. And so if we're thinking again in terms of a company that says, okay, for the first 7 days, we'll charge you only $2,000. And then after the 7 days, since you choose to continue to do business with us, we'll give you a discount where we'll charge you $1,500 per day, right? So if you think of the question from that angle, then you would plug in 7 to represent your first 7 days, and then 12 minus 7 to represent the number of days beyond the 7-day period where the discount would be applied. So 2,000 times 7 is 14,000, and then you would subtract 12, which is the length of time that the project is going to take here, as long as the project takes 12 days, minus 7, which is 5. 1,500 times 5 is 7,500. You add those together, and you get 21,500. That's one scenario where we're getting a discount after the first 7 days. In the scenario presented by the book where we're not getting a discount, so the company is telling you this project, we expect that this is how we bill. We bill by charging $2,000 a day for 7 days. If your project takes longer than 7 days, we're going to charge you the same $2,000 rate plus an additional $1,500 for every day that the project takes, which is usually companies will apply a discount the more you use their service. But let's say that you're working with a company that doesn't give you the discount, then you would go with the scenario that the book presents where you would charge the $2,000 for the full 7 days. And then for the number of days beyond 7 days where you're taking additional time to work on the project, you would subtract that. So 12 minus 7 is 5. You would subtract the additional days from the standard, which is 7. And then you would multiply the extra time or the extra cost by the additional number of days that you're going beyond the 7-day standard. So in this case, it's 5. And add that to 1,500 times the number of additional days that you work, right? So that would be 12 minus 7. I hope it's clear. There are basically two ways to think about this problem, but I would say to you that since the question doesn't specifically say that after 7 days you get a discount, and since the book also presents the information that way, go with this standard of just plugging in 12 everywhere we see D, But just understand that there are two ways to approach the problem. So at least now you know, based on the two scenarios presented, just in case you get an alternate question on the test that says something like, after the first 7 days, you'll be given a discount, then you'll know what to do with the question. So on to domain and ranges when it comes to plotting a function. I want to start by just going over examples of domain and range so that you get comfortable with the concept. And then I'll show you examples of functions being plotted. So this example I got from patreon.com. This graph that you see here represents a function. And this function breaks up, and if you remember lessons when we were drawing graphs on the number line, we represented when we saw a closed circle, we said that that number was included in the range of the graph. And if we saw an open circle, we said that that number was not included in the range or in the domain of the graph. So looking at this graph then, let's find the lowest value for y. If we look on this graph, we see that the lowest value represented by this graph is y equals -4. But even though graphically we can see that -4 is the lowest value representation for the range of this function, looking at the lower half of the graph, so the portion of the graph below the x-axis, the range of this function does not include -4, which is why graphically it's represented by an open circle, and in the set notation form that we see in the green rectangle here, we see an open parentheses. So once again, the lowest value in the range of this function, or in the range of this graph, is -4, but not inclusive of -4. And that's being communicated to us in two different ways here. We see an open circle illustrated on the graph, and then in the set notation form, in the green rectangle, we see an open parentheses next to -4. Okay, and the highest value represented by the graph is at y equals +4, which is also being communicated to us in two different ways. The closed circle, or the circle that's filled in with red here on the graph, so looking at the portion of the graph above the x-axis, the highest point in the range of the graph is at y equals +4. And +4 is included in the range, which again is illustrated on the graph as a closed circle, or a circle that's been filled in. And in the set notation form, so looking at the green rectangle, we see closed brackets after +4, indicative that +4 is included in the range of the graph. So again, two different ways of identifying whether or not the endpoint of the function is included in the range of the function itself. You can think of it, if I can give a sidebar example. Let's say you're standing on this coordinate axis. You're standing at the origin, and you have a large bucket of water, and you spill that water. Okay, and remember, anytime you see arrows on axes, it just indicates that the vertical axis is continuing into infinity, positive and negative. So again, spilled a large bucket of water, right? You know that that spill is not going to continue forever. It's going to be contained in a region that's around the area where you spilled it. So that region that contains that spill is the domain and range. The domain is going to be the horizontal, or the x. If we come back to this example that we're looking at, we know that the lowest value for our function when we're on the y-axis, its lowest value is at -4. But it does not include -4 because we have an open circle. So we're going to represent that with parentheses, okay? So when you see parentheses, -4, you know that the lowest value concerning the range is -4, but not including -4. And then this graph continues up to -2, but we see a closed circle. So we're going to represent that with brackets, indicating to the reader that the range of this portion of the graph continues up towards -2 and actually includes -2. So if we go back to our example on the spill, let's say the edge of that spill is very close to -4, but it doesn't quite touch -4. If you were to draw a straight horizontal line through -4, essentially that means that that spill is very, very close to that horizontal line, but it's not touching it. So that's essentially what this means, is that this graph here, it goes right up to -4, but it doesn't quite touch it, so it doesn't include -4. And then you can see that there's a break. We're still working strictly with the y-axis or our range. You can see that there's a break in the graph. The graph is not connected. It jumps off and it starts again at 1. But once again, we see that it doesn't include 1. So it's represented with an open circle. All right, and then the graph continues and its highest point is at 4, and it includes 4 because we have a closed circle. And so this range is telling us that our graph, let's say that your puddle of your bucket of water that you spilled, let's say that it's a very hot day and it dries, right, in this area, okay? So it's still the same bucket of water, right, represented on the graph, but it happens to dry very quickly in this area. And so we have no representation, or we have no information for that graph between -2 and 1. So we'll represent that by saying that the range of our graph, its lowest point begins at -4, but it doesn't include -4, and then it continues on to -2, and it actually includes -2, so we'll represent that with a closed bracket. And this symbol means union, right? And so this portion of our range is in union with the remaining portion of our graph, which begins at +1 on the y-axis, but doesn't include +1, and then continues on to +4, but it actually includes +4, so we represent that with a closed bracket. So that's the range of our function, or how our graph is behaving along the y-axis, okay? Now let's look at the domain of our function, or how our graph is behaving along the x-axis, or how your puddle of water that you spilled is behaving along the x-axis. We can see that the outer edge of that spill, its lowest point when you're considering the x-axis, is at -6, but it doesn't include -6 because it's an open circle. So you can think of the edge of that spill very close to -6, but not quite touching it. So we're going to represent that with parentheses. And so the lowest portion of our graph is at -6. And then we continue along the x-axis, and then we see that, oops, our puddle dried up a little bit. So there's a separation between the upper and the lower region, if you want to consider it that way, of our graph. But because we have a closed circle here, so imagine that if you picked up this piece and you picked up this piece and you connected them together, this closed circle would fill this open circle, right? So along the x-axis, we know that our domain actually includes -1.
I'm referencing -1 on the x-axis, okay?
So we continue along the x-axis, and we see that our spill stops here at 5, and it also includes 5. So we represent that with a closed bracket, and we can say that the domain of our spill, or the domain of our graph, is from -6 to +5.
-6, but not inclusive of 6, to +5, inclusive of 5.
If we carry that concept along,
the information that the domain and range gives you essentially boils down to the location of your graph and to the identification of all plausible solutions for your function as represented by your graph. So in other words, where can we visibly see that your graph is defined based on its relative location to the x and y axes?
So here we can consider the graph undefined because there's no information between this point and this point. And here, so that's our range. We know that it starts at -4
but is not inclusive of -4,
and it continues up to +4,
inclusive of +4.
but it's undefined between -2 and +1. Okay, that's our range. And then the domain, we can see that the graph continues between -6 and 5. We have viable solutions. And the reason we include 1 here is because if we were standing at this point, right, and we wanted to locate this piece of the graph, this open circle, we would say that it's located at -1 and +1, right? So if you count one space over to the left, we're at -1, one space upwards, we're at +1. We have a solution for our graph, right? Or a coordinate pair for our graph. If we were to stand here and we move down 2 spaces, or let's start at the origin with one space over to the left and 1 space down, we also have a coordinate pair for our graph, which corresponds to -1, -2, right? So in both instances, we have a coordinate pair for our graph when we're starting from the origin and moving left on the x-axis, right? But if we were, let's say we were to start here, okay, at -1, right? And we moved leftwards on the x-axis, so we're at -1 on the y-axis, and then we move leftwards on the x-axis, there's nothing here, or the graph has no solution. So the range, that's why the range of the graph has no solution, but the domain of the graph at -1 has solutions, because we can actually find 2
solutions for the graph at -1 on the x-axis. So looking at -1 on the x-axis, the first solution is the ordered pair -1, +1, right? And that's represented by an open circle. The second solution below the x-axis is at -1, -2, represented by a closed circle. So although there's an observable discontinuity in the range of the graph, okay, so now let's look at the y-axis. The range of the graph between -2 and +1, again, we're looking at the y-axis, which is the home of our range, if you want to think of it that way. When we're considering the domain of the graph, we have 2 solutions at -1 when we're considering the x-axis, which is the home of our domain.
We can find an x value and we can find a y value, right? That would bring us here. But if we were standing here and we moved left, there's no graph, no portion of the graph represented here. And if we were to start here, and let's say we moved upwards, we still couldn't find a coordinate pair for our graph, right? But if we were to start here, for instance, we could find a corresponding y value, and we could find a corresponding x value. And if we were to stand here, we could find a corresponding y value, and we could also find a corresponding x value. At the end of the day, let's say somebody was standing here at -6 and somebody was standing here at +5, they would be covering the entirety of your graph when you're considering the x-axis. But if someone was standing here at 4, a different person was standing here at -4, they wouldn't be covering the range of your graph. Why? Because your graph breaks up along the y-axis. So a different way that you can think of it is match visually the axis that lines up with where your graph breaks up. And the axis that lines up with where a graph breaks up happens to be the y-axis, because our y-axis is vertical and our break is also vertical. Along the x-axis, when you're looking at your graph, there's no break, there's continuity, because we have a closed circle here, we have an open circle here, right? So there's continuity. If you were to bring this portion of the graph downwards, it would join perfectly with this portion of the graph. So along the x-axis, there's continuity, but there's a break along the y-axis. Let's look at another example. For this particular function or this particular graph, let's start with the domain this time. We can see that the lowest point for a graph, or the lowest point where our graph is defined or has a solution, is at -4. along the x-axis. Here's the endpoint of our graph here. And if we follow that endpoint up to the x-axis, we see that it reads -4. Okay, and because it's a closed circle, we're going to represent -4 with a bracket, right? A square bracket. Then if you follow your graph along the x-axis to find its highest point, which is right here, you can see that it corresponds with the value 3 on the x-axis, right? And so we know that +3 will be included in the domain of our graph because it's represented with a closed circle. So again, the domain is the behavior of your graph along your x-axis. So we know that our graph is defined between -4 and +3. So if you had somebody stand here at -4 and you had somebody stand here at +3, they would both be standing on the boundaries or the domain of your graph on the along the x-axis, okay? Then if we look at the range of our graph or its behavior along the y-axis, we see that its lowest point is at -5. And again, we have a closed circle, so we're going to include -5 in our range and indicate that with a square bracket. And then if we move up along our graph on the y-axis, we see that its highest point is at +4.
And so we're going to include that in the range, or we're going to indicate that as part of or as inclusive of the range of our graph using a square bracket, since we see a closed circle at this endpoint.
Again, if you think of this as you stood right here and then you threw a bucket of water upwards in the air and it happened to land and form this shape, the domain would represent how wide that spill was. So it's from -4 to 3, and it actually includes both -4 and 3 because the edge of that spill touches
these endpoint
values on the x-axis, okay? And then the range of that spill, again, you can think of it as being bounded between -5 and +4. And again, that spill touches exactly at 4 and it touches it exactly at -5 along the y-axis. And so we would represent that by indicating that our range is between -5 and 4 using square brackets. Now, if we start to think about the functions that we were looking at, and again, know that a function can be represented graphically. Right? So let's say we're given this function f of x equals x plus 5 divided by x minus 3, and we're asked to determine whether each value of x that we're given is in the domain of f or not. All we're going to do is plug in our values to determine where this function is defined or where this function has a solution. So here, if we go back to this graph, this function is defined along -4 and 3, the domain, and -5 and 4. Why? Because at any point on the graph between the domain and the range that we just specified, if we stand at any point on this graph, we'll find an ordered pair. Okay? Same with this, except we've already discussed that if we were to stand at any point between these two, we wouldn't be able to find an ordered pair. And so this function is undefined or doesn't have a solution between these 2 points where the graph breaks up. So now let's go back to our example here where we're asked to find or determine for each x value whether or not it's in the domain of f of x. All we have to do is plug in the values that we're given. So let's start with -5, okay? So we'll go back to our original function, and everywhere where we see x, we're going to plug in -5. And so here, f of -5 just means that everywhere we see x in our equation, we're going to plug in -5, all right? So -5 plus 5 is 0. A -5 minus 3 is -8. Anytime you have 0 in the numerator, you know that the resultant outcome or the resultant quotient, whatever answer you find is called the quotient. So the resultant quotient or the outcome will always be 0 if you have a 0 in the numerator, right? So 0 divided by -8 gives you 0. So say that -5 is in the domain of this function because we plugged in -5 to get 0. Now let's test the next value, which is 0. So here f of 0 just means that we're plugging in 0 for every instance where we see x in our equation, right? So 0 plus 5 is 5. 0 minus 3 is -3. And so we have -5/3. And so that would be a number that we can indicate, a real number that we can indicate on the number line, right? So we can say that 0 is in the domain of this function. Now let's try +3, okay? So right here on this top portion, we see that f of +3 just simply means that everywhere we see x in this original function, we're going to plug in +3, right? So 3 plus 5 is 8. 3 minus 3 is 0. And we already know that you can't have 0 in your denominator because your answer will be undefined. So 8 divided by 0 is undefined. That's telling you that this, when y is 8/0 and x is 3, this particular function is undefined. Okay, so let me go back to whenever you plug in x into a function, okay, into f of x, it gives you a value for y. So we can consider this -5 as our x, which we see or we established that everywhere where we saw x, we'll plug in -5. So -5 is our x, and whatever value that we get from working out this equation will represent y. So this particular f of 5, the ordered pair would be -5, which is our x value, and the y value would be 0. For this function where we plugged in 0, our x would be 0, and our y value would be -5/3. For this particular function where we plugged in 3, our x value is 3, and our y value is 8/0 or undefined. We don't have a y value. And so we can't plot this portion. And so we can say that f of 3 is not in the domain of this particular function, okay? And again, it's not in the domain because we don't have a solution. We have an undefined value at f of 3 when x equals 3. So if we go back to our definition of domains and ranges in this particular, with this particular function, that it's already been pre-graphed, we're asked what is the domain. Well, you just look again at the graph, at its behavior, and see how it's behaving along the x-axis. And we know that at -6, which is the lowest portion of our graph when we're considering the negative axis or the negative portion of our x-axis, we see that this graph is defined or it has a solution at -6. What we mean when we say that a graph is defined is that you can find an ordered pair for it. You can, at -6, if you started at the origin and you moved all the way down the left-hand side of your graph and stopped at -6, and then from -6 you moved upwards, you would end here at +5, and your coordinate point here would be -6, 5. And so because we have an ordered pair, we have a valid solution, or our graph is defined at this particular point, right? So the lowest point on the domain of our graph is at -6, okay? And the domain essentially represents the x-axis, okay? And then if we move over to the right-hand side, we see that the highest point or the highest value is at +7, right? So if you think in terms of highs and lows, again, remember that we already established that negative numbers are always lower than positive numbers, right? So starting at the origin from this point onto any number that's on this portion of the graph on the left-hand side of your x-axis going on into infinity, any value that you find here will always be lower than any value that you find on the right-hand side, Okay, so we can define the domain of this graph as being between -6 and a +7, and you can see that the circles are closed on both ends, and so we would write that with closed brackets to indicate that -6 and +7 are in the domain of the graph. Okay, and if you wanted to find out the range of this graph or the amount of space that this graph occupies when we're considering the y-axis, you would look for the lowest point, which here happens to correspond with 3, and then the highest point, which here happens to correspond with 8. And you would say that the range of your graph is from +3 to +8. I managed to find an example that was exactly representative of one of the questions that we were looking at, where we were given a function y equals x squared, or f of x equals x squared, right? And so what I was trying to explain is that all you would need to do is make yourself a t-chart, as you see here. On the left-hand side, put in your equation, which happens to be x squared, okay? And then on your right-hand side, you're going to write down y, which will be your outcome of squaring x, okay? And then just choose a set of 5 arbitrary numbers. Always have an origin in your t-chart, okay? So 0, 0, we already know the value of this function at the origin. X will be 0 and y will be 0. So the moment you draw your t-chart, and you've reflected what happens when you work out your equation on the right-hand side. So you would get a value for y, okay? Put down 0, 0, and then plug in 2 numbers to the right of 0 and 2 numbers to the left of 0, any 2 numbers that you want, okay? This particular example, they chose 1 and 2 on the right, and -1 and -2. So let's start by finding the solution of our equation at +1. If we replace x with 1, because at +1 we're saying that x equals 1, 1 squared is 1, right? So when x is 1, y will be 1. If we replace x with 2, 2 squared is 4. That means when x is 2, y will be 4. If we replace x with -1, -1 squared is a +1. Remember, anytime that we square a negative number or we multiply 2 negative numbers by itself, we get a positive number. And we know that 1 squared just means -1 times -1, which gives us a +1, okay? If we plug in -2 into x, -2 squared just simply means -2 times -2, and that gives us a +4. And so now, based on your t-chart, you can plot your points on your coordinate axes, right? So start at 0, 0, and then this is our point 1, 1, right? If we move from our origin, 1 space over to the right on the x-axis and 1 space upwards, we have our second coordinate pair, if you will, +1 and 1, okay? And we got that from plugging in 1 into our equation. Then you look at your t-chart again and plot your next coordinate set or your next coordinate pair, 2, 4. So we're starting at the origin. We're going to move 2 spaces over to the right on the x-axis. Again, remember, we always start with x first. So we're going to move 2 spaces over to the right, 4 spaces up, and here's our coordinate location for 2, 4, right? Then do the same thing with the negative values of x that you indicated on your t-chart, right? So at -1, we're starting at the origin, we're going to move 1 space over to the left. So when x is -1, our corresponding y value is a +1, indicated by this portion of the t-chart here. And then same thing, -2, starting at the origin, we move 2 spaces over to the left and 4 spaces upwards based on our outcome for y. And then you would simply just plot this, you would connect the dots to plot your function. The graph would have a U shape. So if we were asked a graph y equals x squared plus 3, you would simply just plot this portion, do the same thing that we just did, except you would know that this positive 3 means that the graph is shifted upwards, or imagine that somebody's standing at the origin and pushing this graph upwards by 3 spaces. And that's what this positive 3 here indicates. If there was a negative 3 here, you would know that somebody's standing here at the origin and pushing this graph down 3 spaces, pushing this graph 3 spaces downwards. So if we then wanted to define, let's go back to the original. If we then wanted to define the domain and range of this graph, we would say that because we know that the axes continue into infinity, and because we know that if we keep taking values from values of x and adding them to our t-chart, we'll keep getting defined values for our function, we can say that the domain of our function is between negative infinity and positive infinity. That means that when we're looking at the x-axis and we're standing at any point on the x-axis, if we move upwards, we'll eventually connect with our graph and have an ordered pair at that point. So the domain of our graph is from negative infinity to positive infinity, okay? Unless the question, you always want to assume that the domain continues into positive and negative infinity, unless the graph specifies that your function stops at a particular point. In this particular instance, the standard is to assume that your graph always continues into positive and negative infinity concerning the domain, unless you can see that it visibly stops with either a closed or an open circle.
And the 2 arrows indicated on the ends of either side of our U-shaped graph here is further indication that the domain continues into negative and positive infinity. All right, so that's the other indication, or the other sort of sign that you can look out for in terms of the domain or the range of a graph. If you see an arrow at the end of the graph, then it's indicative that that graph continues on into the domain rather of that graph continues on into infinity. If you see a closed or an open circle, then you can make an inference concerning the endpoint of the graph based on the location of the closed or open circle.
This particular graph, arrows are drawn at the end of the graph. So we're going to assume that the graph continues on into infinity. So our range would be from positive 3 into infinity, because positive 3 is where is the lowest point of this red graph, okay? So our range would be from positive 3 into infinity, and our domain would be from negative infinity into positive infinity. Why? Because along the x-axis, this graph just continues on and on, okay? And we'll always, if we were, let's say somewhere here on the x-axis at point negative 1 million, if we moved upwards, we would eventually meet our graph somewhere at a value that corresponds to y, same thing on the right hand side. And so that's why you need to pay attention to what's happening with your graph. If you see arrows at the end of the graph, know that the graph is continuing into infinity. And if you don't see arrows at the end of your graph, like we saw here, okay, or here, or here, you know that your range and your domain stop at certain points along the x and y axes. So here's another example, okay, of plotting a function. We're given f of x equals 5 raised to the power of x, okay, which is the same thing as writing y equals 5 raised to the power of x. And again, you want to start by drawing yourself a t-chart, and then let the left-hand side of your t-chart represent random values of x that you decided to choose, and let the right-hand side of your t-chart represent the outcome of whatever you get when you plug in x or your random values of x into your function. Again, it's easiest just to always start at 0, 0. So you're going to write down 0 on the left-hand side and then pick two values to the right of 0. Here they've picked 1 and 2, okay? And then to pick two values to the left of 0, they've picked -1 and -2, okay? So when x is 0, all we have to do is plug in a 0 everywhere we see x in our equation. So 5 raised to the power of 0 equals 1. If you remember our lesson on exponents, we know that anytime you raise a value or a coefficient to 0, the outcome will always be 1, right? So here we have our first ordered pair, 0, 1, and we can locate that on our graph when x is 0, so we're at the origin, x is 0, y is 1, we move up one space, and here's the location of 0, 1 on our graph, right? Then we go back to our t-chart and let's plug in 1 into our equation. So 5 raised to the power of 1 is 5. Again, we know from our lesson on exponents that anytime you raise a coefficient or a value or a number to the power of 1, it'll just be itself. So 100 raised to the power of 1 is 100. 1,000 raised to the power of 1 is 1,000. 1,000 raised to the power of 0 is 1. 100 raised to the power of 0 is 1. These are two rules for you to memorize and keep in mind, that any number raised to the power of 0 will always be 1, and any number raised to the power of 1 will always be itself. So when x is 1, our y value is 5. We have our second ordered pair. So we'll go to our coordinate axes and we'll plot 1, 5, right? So we're always starting with the x. We're at the origin. We're going to move one space over to the right to represent our positive 1. And then we're going to move 5 spaces upwards to represent our y value. And this point right here on the axis represents our coordinate pair, 1, 5, right? Which we found from our information on our t-chart. Then we go back to our t-chart and we plug in +2 everywhere we see x in our equation, right? So 5 raised to the power of 2 is 25. So we now have our second ordered pair, 2, 25. So we'll go to our coordinate axes. We'll locate 2 on the x-axis, all right? And then we'll locate 25 on the y-axis, okay? So this is 20. The y-axis is an increment of 5. So this is 20. This is 25. So this is our point or coordinate pair, 2, 25, all right? Then we'll do the same with our negative values. Plug in -1 into your equation. 5 raised to the power of -1 is the same as 1 over 5. Remember again, our lesson on exponents, we know that when we have a value or a coefficient that's raised to a negative power, it's the same as writing out that number as a fraction, okay? So 5 raised to the power of -1 is 1 over 5, all right? Which is some very tiny value between 0 and 1, right? So we'll go to our axes and we'll plot -1 and 1 over 5. 1 divided by 5 is 0.2. So let's plot -1 starting at origin. We move -1 spaces over to the left, and then 0.2 spaces up on the y-axis, which is a very tiny movement, okay, between 0 and 1 on the y-axis, right? So this is our point, -1, 1 over 5, or -1, 0.2, okay, if you plug in 1 over 5 into your calculator. All right, then you do the same thing for -2. Everywhere where you see x, you're going to plug in -2 into your original equation. 5 raised to the power of -2 is the same as writing 1 over 5 squared, okay? So again, when you're dealing with negative exponents, all you do is add 1 to your numerator, and then your denominator will just be the positive of your exponent. So in this case, we had 5 raised to the power of -1. So we add 1 to our numerator, and our denominator is going to be 5 raised to the power of 1. Here we have 5 raised. So we'll add 1 to our numerator, and our denominator is going to be 5 squared, okay, which is 1/25. All right, which is again another very tiny number between 0 and 1. All right, so we're going to indicate that on our coordinate axes. Our x value is a -2, and our y value is a very tiny number that's between 0 and 1. Here's 1. 1/25 is going to be a very tiny number between 0 and 1, and you would indicate that here, where this is -2, and this is a very tiny movement along the y-axis, okay? And then once you have your points, you would simply just plot them on your coordinate axes, and then you can determine the range. Since this graph indicates or has 2 arrows at the end of our function, that indicates that this graph continues on and on and on into infinity. So we can say that the domain of this graph is from -infinity to +infinity when we're considering the x-axis. And then we can say that the range of this graph is 0 to +infinity, but this graph, if you keep plotting negative values into this function, you'll keep getting really tiny values of y, very, very close to the x-axis, but never touching it. So you would represent that with an open parentheses, 0, comma, +infinity, which you would represent with a closed parentheses. I should say that anytime you see, I don't have an example here, but anytime you see a graph that ranges from -infinity to +infinity, either on the x-axis or on the y-axis, right? You always want to represent that with parentheses, all right? And that's just because we don't know the exact value in infinity, but we just know that the graph continues, right? We don't, infinity is not a number that we can, so a discrete number is a number that we can identify, like 10, 5, 4. Okay, those are discrete identifiable numbers. They're finite, they're countable. Infinity is not countable, right? So you would represent that with parentheses, not square brackets, right? Which square brackets is for values that are definite or countable. And the domain of our graph is from -infinity to +infinity, and would represent that also with open and closed parentheses, okay, not brackets. Let's now move on to today's lesson, okay? All right. Oh, I have one more example. Do you want to do one more example?